started on this lecture today. So the DC motor performance in steady state. So brushed DC motor performance has several aspects, but most of them revolve around the so-called motor curve. Motor curve is for a given motor voltage, its steady state speed versus a constant torque applied to the load. Okay, so let's actually break that down for just a moment. So, typically this constant voltage that's applied to the motor, most often is its max voltage, but that's not always the case. People do other motor curves in this. But so if you do the max voltage applied, and you have no torque being applied to the output of the motor. So this thing's disconnected from any load. It's just you put on full voltage and no load on this thing. This motor is going to speed up, right? And it's going to actually speed up to its maximum speed, okay? And then if you apply a torque, which usually is done by applying a brake, okay? You start applying a brake to it that creates a torque that resists the motion. It slows it down a little bit, okay? And then if you apply more torque, it slows it down more. It slows down more and more. And these measurements of the velocity, when you change this torque, the brake essentially, is the so-called motor curve. That's the sort of fundamental curve that's used to represent how a DC motor works. Okay. We're actually going to predict the motor curve for our motor. It wasn't given in the spec sheet. They didn't give us a motor curve. So we're going to actually draw a motor curve for it. It's pretty fun. So the test setup for drawing such a curve requires a calibrated controlled torque source applied to the motor shaft. A brake is typically used. A voltage-controlled magnetic particle brake is ideal. So you can actually get these really cool devices where you apply a certain voltage and it'll apply a torque that's proportional to that voltage, that's calibrated and you know how much it is. Doesn't matter how fast it's going, it'll apply the same torque. It's a pretty sweet device. So anyways, if you're interested in that, I gave you a couple links in the footnote. We will gain a deep understanding of DC motor performance characteristics only by tarrying with this situation. Okay, so this test setup. And a lot of people, I think, don't have a good feel for how these motor curves work because they never have actually analyzed how do they generate these motor curves. Therefore, we will begin by modeling it in section 4.5.1, which we're just going to cover today in just a couple minutes, and then next time analyzing its performance in the next section. So modeling the test system. So we're going to come up with a model for it. Including a torque source on the load changes the model only slightly, as shown in this linear graph. So the only difference between this linear graph and the previous linear graph is that now instead of having the B and the J be for the entire apparatus, now the B and the J are just for the motor. Okay, so the motor has some damping and the motor has some and the rotor inertia. So those are what those are now, and they're not combined with those other components. And now we're applying this brake. So this brake has to have a torque source to model it. So that's why we put the torque source on there. Notice that things that didn't change. One thing that didn't change is the normal tree. It's the same. And actually, the state variables are the same. Nothing changed there. The first thing that's changed when we do the modeling of this is the input vector. The input vector now not only has the voltage source, but also has the torque source. So our input vector is not just Vs, now it also has Ts in there. Two inputs. The continuity equation for the inertia becomes, instead of, it was before that torque on the inertia was negative T2 minus B, TB. Now it's also minus TS. And the reason it's minus, I mean, it's actually, the reason it's minus is that we drew the arrow that direction. But we drew the arrow that direction, which is actually unusual, right? We drew it away from the node of application. So that means our coordinate arrow is actually opposite this torque source. But it makes sense because our torque we're applying is specifically, it makes sense that it's negative, right? It's going to be opposing the motion. It's a brake. It's always opposing the motion. So we say that the motion that it's going to be turning, the output of the motor is going to be turning in this problem, is positive, and the torque source is actually connected opposite to that. So it's going to be negative T2. Negative TS. And finally, the state model's matrices, B and D change. So A and C also change, but they only change in that B becomes BM and J becomes JM, etc. Right? So everything else about A and about C are the same. B and D are very similar, but they actually each get a new column, right? Because B and D are multiplied by the input vector U, which now has a new value in it. So they have a new column. So the new column in B is this, and the new column in D, although we have it as a row here, the new column in D is this, essentially this column. And where that comes in is you can see the negative show up there. It's coming in because of this term in that equation. But otherwise, everything else is the same. And I actually also included a file with the website file for modeling this too, if you want to look at that equation. It's also attached to the PDF. And the next time we'll get into the steady state performance analysis, we'll be using MATLAB for it. So, looking forward to it. See you guys on Friday.